Okay, so welcome back. We're going to be doing this second video, or basically the next video in Unit 5. Sorry, Unit 5, and that's thermochemistry. So if you've been following along in your textbook, like I highly recommend you should, you'll see the next section that we have to cover is we have to cover the basically enthalpy change enthalpy change of combustion. So this is again just a unit where you mainly have to use your textbook. Is that the enthalpy change in combustion, the term that we use for it, remember in the last video we did delta H of F, and that's the enthalpy change of formation from its elements in their standard state. So what that meant was that, our delta H of F was basically, if we did that with CH4, you basically break this CH4 into its elements, carbon and hydrogen. You write how they exist at room temperature, so it's a solid and a gas, and you write the reaction as if it was happening that way. So our delta HF naught, which we got from our chemistry data booklet, is equal to carbon solid plus hydrogen gas reacting to form CH4 gas. So basically, this value will be an experimental value provided to you in your chemistry data booklet. Whereas our delta H of combustion, it's almost the exact same thing. So our delta H of combustion, it's going to just simplify us not having to do this delta H of F calculation, and it's more accurate. Let me just write it down. I'll say it'll be our most accurate because this is the exact experimental value. So it's the most accurate value we can get for combustion because it's the exact experimental value. So scientists that actually ran this experiment in a calorimeter and figured out exactly what our change in energy is, our change in enthalpy is. So that's why we wanted to, for combustion reactions, if the question ever talks about combustion reactions and something to do with our delta H for it, what you have to use is you have to use your chemistry data booklet again. Chemistry data booklet. And this is provided to you in paper 2 and paper 3. And this is in section 13. Section 13 of your data book. So let's go to the data booklet really quickly and you can see it. So right now we have the energy change of combustion at room temperature. So right, this symbol up here, this symbol right here means in standard conditions and standard states. So in standard conditions and standard states, what this means is the standard states is what phase does it exist in at standard conditions. The standard conditions, like I said, was 25 degrees Celsius, which is 298 Kelvin in the last video, and 1 atmosphere pressure, 1 kilopascal, 100 kilopascals, 100 kPa. So basically, so it means the same thing in this case. So it's every time you see that symbol, it means in standard conditions, in standard state. So what these values give you is it gives you all in standard state. So they reacted it in the calorimeter at 298 Kelvin at exactly 1 atmosphere of pressure at 100 kilopascals of pressure, and they solved what was the energy change of the combustion. And here's the exact experimental energy changes of combustion when we react different things in a calorimeter, when we burn graphite in a calorimeter, when we burn carbon monoxide in a calorimeter, we burn pentane, so it's when we burn all of them in a calorimeter. So basically, this is just another value that's you need to know is given to you in your chemistry data booklet, and basically, it's the most accurate because it's the exact experimental value. If we did, right, we can do the calculation like we used to do, right? We can calculate delta H equals the sum of the bond energy of reactants minus the sum of the bond energy of products. But this is less accurate than this, right? This is experimental. This is the real value that the scientists calculated. And this is the theoretical, right? If we have a carbon-hydrogen bond, let's say we've got CH4 versus CCl. So in these two cases, right, what this does is this assumes that this carbon-hydrogen bond is the exact same as this hydrogen-carbon bond. And the reality of it, right, in reality, we know that they're not the same. This one's got a strong delta negative and this one's got a delta positive. So that's going to have an effect on this bond strength. In this case, right, we've got a carbon-hydrogen bond. There's no delta negative. There's no delta positive. So in that case, the electron distribution in the entire molecule is different. So basically the takeaway from this quick video, just to introduce the enthalpy change of combustion, is to know that it's in standard state, it's combustion, and it is more exact than if we dealt with any other values, right? We could also calculate this if we did, like CH4 plus O2 reacts to form CO2 and H2O. Let's see how we can balance this. There, double that. So we can also do that, right? We can also calculate our delta HF naught by just doing the sum of the delta HF naught of the products minus the sum of the delta HF naught of the reactants. So we can find it in multiple ways. But like I said, the most exact way is, of course, to use the exact results. So there's multiple ways. So it depends, right? You have to look at what the question wants. If the question says, solve the enthalpy of the reaction by using delta HF naught, that means you have to use your delta HF naught values given in section 12. If the question says, one of the questions might just say something like using the delta H value. So this is for HL, right? For HL, we're going to be doing Gibbs free energy, delta H minus T delta S. Then you actually, you'll need to look up the enthalpy of combustion, because the enthalpy of combustion is what you want to plug into this equation in order to get the most accurate Gibbs free energy. So, the question should give you some guidance for what to do and how they want you to calculate it. So aside from that, give me 1 second. There's one more thing I'd like to cover with you guys before we finish up for today. And the last thing that I want to cover with you guys is different ways of writing it. Two ways of writing it would be, let's do methane. We already did that. Plus O2 reacts to form CO2 and H2O. Double that and double that, and we're fine. And just add the states. Gas, gas. So don't forget to do that, because I've seen lots of questions that you lose a significant amount of points for that. So we can give it in two ways. We can give it for the data table. If we go down here, the methane, negative 891 kilojoules per mole. So right, if we have, so that can be our delta HC naught. But also the question could write it in another way. This is written with a negative sign, so we know it's exothermic. But the question could also write it like this: CH4 gas plus O2 gas reacts to form CO2 gas plus 2H2O plus 891 kilojoules per mole. So these are two ways of writing the same thing. Right? It's reactants, and it's products. So you can consider this as a product. You have 891 kilojoules. So in this case, it wouldn't be kilojoules per mole because it would be a stoichiometrical equation. So if you had half a mole, it would be half this value. If you had 2 moles, it would be double this value. So plus 891 kilojoules. So that tells you how much energy is released as a product. So it's writing the exact same way. It's writing the same thing. It's a product. It's released this much energy, and it shows that it's released that much energy. So there's two different ways of writing it. And that's about all we have to cover for today. The last thing we're going to cover is just a quick definition. Now that we've talked about the enthalpy change of combustion. And the enthalpy change of combustion, delta HC naught, is equal. What it is the combustion. It's the heat evolved from the complete combustion, so that that could be an important word, a complete combustion of, and here it is, 1 mole of substance. So right, complete combustion means that for this type of question, O2 always in excess and of 1 mole of the substance. So right, 891 kilojoules per mole. So that's per mole. If we had 2 moles of substance, 2 moles of methane now burning in the air, we'd just double this. We'd have 16, let's see, where's my calculator? I got it open still right here. 891 times 2, we have 17. So this is for 1 mole. And for 2 moles, we had 1782 kilojoules per 2 moles. Or, we can do anything. We can go half a mole, a quarter of a mole, 0.1 of a mole. We can do whatever we want and just change it respectively. It's this many per mole. So if the question says, you have 1.18 grams of methane, what you do is you convert that to moles. So 1.18 divided by the molar mass of methane, which is 12 is 16 approximately, 1.18 divided by 16. And 1.18 divided by 16, we've got 0.074. 0.074 moles. So if we were to figure out how much energy is released from combusting this, you take how many moles you have, multiply it by how much is released per mole. So let me just erase this down here. We don't need that anymore. So you take 0.074 mole multiplied by 891 kilojoules per mole. And we see the units cancel out. Kilojoules, mole over mole, moles cancel out. And what we're going to have is 891, this times 891, 65.71. So you have 65.71 kilojoules of heat released. And that would be your final answer. So see, they can come at you with a few, either simple questions, and all you have to remember is use my data booklet. Data booklet. So really remember to become accustomed with your data booklet. So okay, I hope this video was useful. I'll see you in the next one.